Any questions? All right. I do have your exams. I'll hand them back at the end of class. Overall, on the exams, just so you know, people did well. The average was 83%. Median was 85%. So roughly 30% of people got above 90%. Another 40% of people got above 80%. So you'd say 70% of people got A's and B's, roughly, on the test. So those are all good numbers. Not for everybody. Some people didn't do as well. What's interesting is some of you who did really well in the first test didn't do as well in this test, and some people who didn't do as well in the first test did better on this test. So we'll see what happens when it's all done in the end. All right. More on software security. We're going to talk about, okay, we're not going to talk, let's be honest. I'm going to lecture about some processes in dealing with this. This is, understanding these processes is very important for knowing how we deal with building more secure systems. And this can apply not only to software systems, but to network design, to business processes, et cetera, not just software. So to think about that when you're looking at this. And of course it has to. So, but some of this, of course, is very much software related. I didn't cover this last time, right? My mind's gone, so I'm old. Okay. Our binary files, the executable, the programs produced from source. There's two things, what we call compilation and interpretation. In compilation, we take our files, and there could be more than one of them, with our human readable C code, maybe some additional information, what we call header files. The C preprocessor, this is for C code, takes the data in the header files and the source file to generate one large file, and then it compiles it. Compiles it, it usually creates it into an intermediate representation. Sometimes that's assembly code, sometimes that's some other type of representation. Sends that, so what happens is we can take this and generate this intermediate representation here. And then depending on which machine you're doing, if you're an Intel processor, ARM processor, whatever, the assembler converts that intermediate representation to the right format for that particular processor. Even if it's a 32-bit Intel versus 64-bit Intel, the outputs are different. So this assembly process takes the standard machine independent representation here and turns it into a standard representation, a machine specific representation. These are independent object files. So in Linux, we use the ELF file format, which is executable and linking file format. Windows uses the PE format. I don't even remember what program executable or something like that. Oh, just because it's fun. So ELF is the executable linking file format. If you want debug information in there, it is stored in there in what format? The debug format, right? The dwarf format. Debug, writing, whatever. I don't know what dwarf stands for. Because why? Because computer scientists are nerds. Okay. We take the object files, combine them together with any standard library files, and create our executable. The default name of that is a.out, but you can rename it anything. So that's the compilation process. The interpreter process takes the program, the source code, one line at a time as the computer is running the program and executes it. Now, and figures out what to do and does that. Now, sometimes it says, hey, I know I'm going to be doing this multiple times. Let's turn that into the actual execution code, store that somewhere and just run that instead of reinterpreting. That's just-in-time compilation is what we call that, or JIT. knowing what these are and how this works is important at some types of cybersecurity analysis. I'm going to step away from this though and go back to what we actually want to do. We want to audit the code. Okay. And how we do that is we want to do a complete assessment of the code, because we're looking at something like this. And for some reason, these slides look familiar, like I've talked about this before in this class, but I'm probably thinking of a different class. Right? I didn't show these?
I think you did.
You think I did?
I remember the first this one.
Some of this I've showed. Did I show this before Thanksgiving?
That was a long time ago.
Some of it, yeah.
Some of it. So I'm going to go through it fast because all of a sudden it's like, this is looking familiar, but my notes said I didn't. So we have the application handling. So our source code, don't worry about what this is. What we have to do is, yeah, I did do this. Okay. Wow. Anybody have their notes where I ended? Obviously, I had the wrong notes myself. I don't want to spend days covering the same stuff. Nobody? Hmm?
We didn't get to the third one, documentation and analysis, but we got to application review. Maybe not all of application review.
Okay, let's just start at application review. Okay, so I'm going to go real fast then. Pre-assessment, scoping, what's the goal? What do you have? Let's figure out what you got. Do you have just the source code, the binary, the executable, etc.? What are you supposed to look at? Are you only looking at security related modules or the whole thing? How much time do you have? Some code's harder than others because it's complex. So you collect information, you talk to the developers, you interview them, you get their documentation, anything they wrote down, you get standards that they have to follow. Then you review the design of the document. It's very useful for prioritizing and scoping. Because you want to say, okay, here's this whole thing you're doing, but we're only doing the security relevant functions. What are they called? Where are they? What security do we do? What standards do we follow? So we looked at design documents for that, if they have them. May not have design documentation. There are two places I've seen where their design document is a whiteboard. As they're going through their agile development, they put the stories. This is what we want to do. When they're done, they erase it and go on to the next part. And maybe or maybe not, they took pictures of the whiteboard. Or if it was a smart whiteboard, they stored the images. The design documents may be outdated. Might be third party involved who doesn't want to share their own documents. Developers change jobs, clients don't want to pay for things. So what we want to do is avoid drowning. You want to avoid getting lost in the details. You want to avoid going down the rabbit hole. So what you want to do is use different techniques and switch between them when you're doing your reviews. One is people can only intensely concentrate for a limited amount of time on something. So you switch what you're looking at. I'm looking at the code. I'm looking at design documents. I'm doing an interview. Different vulnerabilities require different perspectives, different ways of thinking, different ways of looking at a problem. Variety helps you maintain your discipline, maintain your motivation, and different people think in different ways. And because different people think in different ways, you got to start worrying about things. And context matters. Life experience matters. Okay, for example, and I was tired this weekend, I know. So I got a message about a charge. Oh yeah, I was on my iPad and up pops an alert, hey, Ziply Fiber charged so much to your credit card, automatic payment. So what was my thought? What would be your thought? It says Ziply Fiber. What?
Who's Ziply Fiber and what do they sell?
Who's Ziply Fiber and what do they sell? Yeah, so Ziply Fiber does internet, phone, other things in this region. My first thought was, oh, my wife bought some more yarn. Because she buys a lot of different yarn from a lot of different places. She's an avid knitter. And it pops up. I'm not thinking Ziply as being the internet thing. I'm thinking fiber, not fiber optics, fiber as in knitting. Because I know she's looking for a new project and she was shopping for things. Context matters. And that's different ways of thinking of things. And you think, oh, of course you know what it is. No, I know what it is. Doesn't mean you know what it is. A developer develops something. Well, that's obvious to everybody. No, it's not. Okay. You need to have an iterative process when you go through it. You need to have a plan for auditing the system. Is it secure or not? You need to develop your plan, then do the work, then reflect on what work you did. Did I find anything interesting? Was I getting lost? You know, tell yourself, hey, I'm gonna focus on this for a couple hours. Now let's step back and think. Was I spending too much time on one thing that really didn't matter? When I'm doing this analysis, was I stuck? Maybe I'm never going to find a vulnerability there. Move on. Or yes, I took some notes and this thing was really important. I kind of put it to the side. I need to focus on it now. I'm finding something really interesting. There was a obvious disconnect between what the developer was telling me and what the code is doing, or what the design document says the code should be doing. The developer was thinking here, you know, nobody's going to have a problem. This is an internal system. Everybody's trusted. And over here, oh no, it's got a web interface and everybody's using it. So for the plan, get your bearings, figure out what the scope is, what the system is, who are the developers you have to talk to, what are the design documents. One of my former students, this is what she does or was doing. It's been a few years since I've talked to her for her career. She actually never looked at the code, but she always put together the plans for doing security analysis, got her bearings, decided what needed to be looked at, and then kind of allocated things to the team. Oh, you're going to look at the code. You're going to look at this. You're going to look at this. Here's our meetings, bring things together. She worked for the Office of the Inspector General for the United States government and did cybersecurity analysis, a whole bunch of different computer systems. So they looked at an IRS system. They looked at a website for somebody. They looked at spy satellite software. Those are the three she was telling me about when I ran into her at this conference. So, which says you do this stuff, you get your bearings. Decide on the review structure. Is it top down, bottom up, hybrid? We'll talk about that. What is the general application's purpose? You know, figure this out. What is the software supposed to be doing? What are the assets? You know, what resources does it control? What are the entry points into the software? How do people communicate with that software? How does it interact with the outside world? What are the different pieces of it? The components and modules? How do they relate to each other? So now you're starting to get down into the weeds. What are the fundamental security expectations? And this becomes an important thing when you're looking at this, because some people, or a system may be designed to share information without any security expectations. Or there may be an assumption that everybody who accesses the system through this particular interface is already authenticated. There may be, oh, we assume the underlying system is doing all the cryptography for us, so there's not a problem. I know we had one where we had data, US government data that was on a server that the only people who could access it were people in my lab. And we had restricted network access. Well, the sysadmin decided to move it to a different server, which now had public access. I did get a phone call the next morning from the NSA saying you have these for official use only government files on a publicly accessible website. It was a hidden URL. They didn't even have a link to it, but they found it because they're the NSA. And I said, wow, I know it's on an isolated server. Let me check this out. Found out what happened, told them. I said, I'm sorry, I'm glad you found it so fast. They said, well, if we found it, everybody else did. So we got in trouble. But the expectations, we had a fundamental expectation. I should have encrypted it. This was back in 2002, 2003 timeframe. But I thought, you know, we had an isolated network. I was good. Somebody opened the floodgate. You know, what are our major trust boundaries? That was, I assumed we had an isolated network and network access control, and that was wrong. Was there backup? No. Was there defense in depth? No. Why? Because I screwed up when I set it up. I didn't even have password access protection to it, which I should have had an extra level. We didn't get in real bad trouble, but and 2 years later, all that stuff was publicly available. Anyway, it was, you know, what we were looking at was the pre-release version of this. So, but think about these. Think about how people can misuse them, misconfigure them, and when you start looking at the system. Okay, so now the plan, you decide on your audit strategy. How are you gonna look at this, top, bottom, bottom up? What are your goals? And pick the right strategy. I'll talk about those. Create a master ideas list. Hey, these are things I have to look at so you can go through and check them. Lists are good. I'm not saying you have a checklist that you follow, and once you're done with that checklist, you're done. The checklist gets you to focus and gets you started. Okay, because too many people I know have done security audits. Hey, we satisfied everything on the checklist. I think I've explained this one once where somebody was, analyzing a place which said, do you have a firewall? Check. It wasn't on the checklist. Does the firewall have rules that says to do anything? Nope. There wasn't on the rules, so it didn't. The firewall just acted as a gateway to the internet and allowed all was the default rule. Well, because it slowed us down if it did anything else. And the checklist didn't say we had to have anything about rules. And unfortunately, at that time, the default on the firewalls was allow all, not deny all. So your master ideas list, these are things you start looking at. Check the firewall, check this, check this. What is the security? What is access control? How are things protected in storage, transit, processing? What needs to be stored? That type of thing. Pick a target, coordinate with others. All right. So that's your planning part. I'm skimming through this. There's more details on this in a later class. You work. So I've done the plan, now I do the work. Take notes. These are your working papers. Helps you stay organized, ensures proper code coverage. Remember where you keep your notes. Make sure your notes are organized in some way. It is fine to use electronic notes. It's actually probably better. I know, back when I started doing this a long time ago, it was a lot of paper notes. It was a notepad and we just flipped pages. It was hard to search. But electronic notes can also easily be deleted or overwritten. Hey, in so many places in my computer systems, I have files called notes. That's just the name of the file. And if I'm on a research project in a subdirectory, in that research project, I create a notes file. I have accidentally overwritten it with another notes file, copied it from one directory to another. And the system says, okay. And then it's gone. Keep them updated. Dates in there, times, other things are really useful. So easier way to transfer the knowledge to others and coordinate work. Your clients will expect detailed documentation, so you can take your notes, your working papers, and merge them into a standard template. And we'll show some of this later, or I'll show some of this later. Your application may require follow-up reviews. Some of the reviews may be, okay, these are the problems, security problems we're seeing now, you need to fix them here, and that's your follow-up review. Or maybe we think there might be a problem here, somebody else has to look at it in further detail. It should be clear enough. Others could approximate your work. I looked at this, I did this, I evaluated this, I tested this. They should be clear enough for you to use if there's a large gap in time between visits to that part of the code. Hey, I'm working on a research project. We developed something. I stopped. I worked on something else. 6 months later, I go back to it. What was I doing? There's one I was working on recently. I'm trying to figure out, I know we did this. We ran experiments. I know I wrote notes on doing these experiments, so I know how to redo this. I can't find the notes. Why? Because I can't find which machine I did the experiments on because I ran it on. We have all these different VMs and it was on some VM on some machine somewhere. That's my bad. This was 18 months ago we were doing this project and I thought we were done and now we need it again. So you have, when you're doing an audit, it's hopefully not an 18-month audit. So that hopefully you can keep all these things, but keep them well organized. Do as I say, not as I do. Notes should be clear enough to establish code and vulnerability type coverage. What code were you looking at? What vulnerabilities were you looking for? So we can say, okay, you checked all this code for buffer overflows. You checked all this code for illegal access or authenticated access or encryption or other things. Avoid falling down those rabbit holes. What do I mean by this? And you can answer any way you think is appropriate. What do I mean by avoid falling down the rabbit holes?
You get chasing something and you think it's going to be there, so you keep digging. and you think, I dig into this and I do enough research, I'm gonna find this. Insert X, right? No matter what class you're taking, what X you're working on, it's there. Personally, I like timers.
Yeah.
When I'm starting something new, give myself 10 minutes to dig down the rabbit hole, or 5 minutes, or whatever it is. And when that goes off, it's a reminder to me to re-examine as to whether or not this is worthwhile.
Yeah, exactly. You can go down that rabbit hole, you can get lost. You can be digging and digging, trying to find something, and it's not there because it's moved on. Now you can think about this actually following a rabbit into a rabbit hole. You can think about it as Lewis Carroll and Alice in Wonderland, and you can get into some really interesting stuff. You want to avoid this because you could spend a whole lot of time for a whole lot of nothing. Okay. There's a quote I used to have up in my research lab. It isn't enough to be busy. The ants are busy. What we're busy doing that matters. You know, and I've had people say, well, I spent hours and hours and hours on this. That's nice. And what did you do? You know, I have a student who's working for me right now who I keep asking that question. I'm at the point where that student will be working for me much longer because I keep asking, what are you doing? Well, I'm spending time doing this, but where are the results? There are no results. We need results. The sponsor needs results. We need to do something. I think they're going down rabbit holes, trying to explore different things that just aren't working. Take breaks as needed. Give your mind a rest. Give your hand a rest. I think I mentioned before break that I had sprained my thumb and it was hurting. It's still hurting. And going through these exams, trying to add up your grades, turning page after page. I am so left-handed when it comes to certain things. I'm normally right-handed. That's my dominant art. But I do so many things with my left hand that I didn't realize how many things I need to do with my left hand. Which is a different perspective of things too, when you think about it. So, all right, reflect, step back, review, update your notes. Status check. What have you learned about the application? Write it down as you're going through. Oh yeah, that was interesting. Write it down. Are you focusing on the most security relevant components? Did you get lost? You know, I spent all this time doing this thing. I remember one analysis we were doing. We spent a whole lot of time analyzing this piece of code. And then we realized it was wrapped by a security function. So we didn't have to worry about the security. All the checks were done elsewhere before the code was called. I think I gave the example, a faculty member here was doing research on the primary avionics system for the space shuttle years ago. And they found a bug in the code and they gave it to NASA and NASA said, nope, we're not fixing it. And they said, but it's a bug in the code and it will crash the system or it'll cause a problem with these input parameters. And they said those input parameters only exist when the space shuttle is not going up, but is going at such an angle the wings are being ripped off by the forces on it. And at that point, we don't care about the computer crashing anymore. It will crash with the rest of the space shuttle. So they'd rather not fix code they knew worked in the bounds of what it worked. I had a friend who worked at the Air Force, same thing. They did an approximation of software. He said, but here's a better code for the software at these, beyond these bounds. They said, well, it's physically impossible. The physics say we'll never get there. So we're not going to fix the code. That type of thing happens. Have you gotten stuck on any tangents, gone down any rabbit holes? Move on. Does your master ideas list have many plausible entries? These are things we want to really look at. Are they plausible? Are they reasonable? Have you been taking adequate notes, record enough detail for review purposes, and look at it and say, you know, I was spending so much time focusing on this code, I forgot to take enough notes. Let's go back, write down what I remember, and remind myself to take notes in the future. If you don't reflect until 2 weeks later, you may miss too many things. One person I know, a friend of mine who does this for a career, he says at the end of each day, he reflects. He spends a little time. What did I do today? What did I learn? And double checks. Did I take notes or did I do this? Actually, he used to do this for a living. Now he's retired and a millionaire, so it doesn't matter. If you're working from application models and documentation, do they reflect the implementation accurately? So that's another thing. Okay, I've looked at the application, I've tested the application, I've reviewed it. I have the models of what's happening, I have the documentation of what's happening, and here's the reality. Do they match? Reevaluate. Okay, I've reflected now. I was using a top-down approach, which I'll talk about. What if that failed? Maybe I try a different approach. Top-down, look at the big picture of the system and slowly break it down to pieces. Bottom up, you look at the individual software components, modules, and build back up. Or were your goals correct? Maybe you thought, hey, I was going to look on this and this, and you find that's not really the relevant thing. Did you understand the application? You get into it and say, wow, I thought it was doing X and it's really doing Y. What if you found a vulnerability? Are you done? No. What if you didn't find a vulnerability? Are you done? No. People like to say, hey, we had an expert evaluate our code. They found nothing. Other people say, oh, we found the bug. We found the bug in the system. We're good. You know, human nature, you want to be done. Have a team partner review your work. Maybe they have different ideas, especially they look at your goals, your scoping, etc. All right. Then you have to document the results. What was the threat? Actually, do I have this? What's the threat that you're worried about? What was the location of the vulnerability you found? What class was it? You know, and there's different types of vulnerabilities we look at. A memory corruption vulnerability, release of data vulnerability, those things, describe it. What had to happen for that vulnerability to be exploited? Maybe somebody had to have a weak password. Maybe somebody had to have configured something wrong. Maybe it just the system had to be running for so long. What's the business impact? What's possible remediation or mitigations to fix it? What's the risk? What's the severity, probability? These are all things we can look at. I'll talk about this later in the next section. So let's see. Let's go into some details of some of these. Code auditing process, pre-assessment. What is the goal? What is your timeline? What do you have? Source, binary, a checked build, a true black box. So source, I have the source code. The binary, I have the executable. A checked build, I have something that was evaluated that has some extra documentation, some other things in it that is for the internal testing of the product. True black box, I have what's shipped to the customer. And that's all I can look at. What information do I need to collect? And is it available? Interviewing the developers, looking at developer documentation. And then the plan, the application. Actually, what is going to be my audit strategy? Coordinate with others, pick a target, take good notes. So some of this is what I just talked about. Avoid drowning. Don't go down the rabbit hole. Reflect, iterative process, document your results. Okay. So if I'm looking at code and if I'm auditing the code, there are two main strategies that people use. What we call a code comprehension strategy and a candidate point strategy. Code comprehension, you want to look at all of the code. You want to understand what it's doing. So it's comprehensive. You analyze your source code directly. The idea is to discover vulnerabilities, improve your understanding of the code. What does this application really do? This is hard when it's a very large application. It is a very, very useful skill to be able to look at somebody else's code and understand what it's doing. It is hard to look at somebody else's code and understand what it is doing. It is hard to pull out something in the middle of a document or middle of a function and say, oh, here's a useful function, but who calls it? What is it? You see all these variable names. You see all these classes and structures and other things they use that you know nothing about, and you got to expand up and down. But you really get to, if you really get to know the software, you can understand and start to get a feel for how things flow and where the vulnerabilities might be. Candidate point strategy, you pick potential issues and you examine source code to determine relevance of those issues. Oh, I'm worried about inappropriate use of encryption, like incorrect or insufficient. So let me look at where the code does encryption. Let me find who calls the encryption routines. I'm not going to look at the whole function, the code. I'm not going to look at everything it does. So again, you look at something like this, here's a MSLS handle application. Server state, client context. Okay, here's some debug print. And if, you start looking at this, so what's going on? What is happening? So you have to read this code, you have to understand it. Okay, so I've got current state, I've got a client context, so this is a connection I'm dealing with. I'm handling something, but I don't know what. Handling an application message, okay, maybe that's what it is. Here's the message length, okay, I know its size. If it's less than the header length, remember when we talked about network protocols and their headers? If my message length is less than the header length, I got a problem. It's not long enough to be a message because every message has to have a header that's appropriate. Got that. So that's a good check. Now I grab the message and I convert it to the right type. And then I say, hey, here's the message type. Here's its length. Good. And now based on type, I do things. So here's one. If it's an application type list board, I love all these debug prints in this one. Then I can start looking, okay, it's an SLS message, response, allocate some space. So I can start looking at things that I know about. Where would I have a problem? Okay, I've got some size ups that possibly is an issue. I'm allocating space. Do I unallocate it later? Those are things that I look at, etc. I'm going through looking at the code, trying to figure out what it's doing. Okay, this is managing messages, looking at different message types. One thing I would look at is what different message types are there? Does it cover every single one? What does it do when that's not a valid message type? But I start looking at that. Take good working paper, take breaks if needed. Okay. So one technique that people do when this code comprehension is we look at what if this was malicious input? What if this message that I'm processing was an attack? How does it flow through the system? How is it used? Okay, I'm noticing here, for example, it is saying, give me the message length. If this message length is less than this. Now, I happen to know when I talked about things earlier, SLS application header length is probably a size of type thing. It's an unsigned integer. If this message length happens to be an assigned integer and somebody put a -1, that suddenly becomes a very positive number and this always passes. So it's always never less than that and we move on. If it was malicious input, I'm going to check some data types. So I start following through. Now we're using the message. Okay, it's malicious. It's now stored in this app message that I'm using later. Where could things go wrong? So that's the first thing. You just trace the user input. We assume non-user input from other parts of the code that was generated by the code is okay. We're not worried about that. We're worried about the user forcing it to do something wrong. So I started a data entry point in the system, search for any type of behavior that appears unsafe with respect to this. Keep the set of malicious input in the back of your mind as I read the code. Okay, so that's one comprehension strategy. How is the code working dealing with all this? And there's many, many different ones of these. So we discover vulnerabilities, directly analyze the code. You have to read the code, need good working paper. Advantage, have a better view of the program, catch some subtle problems. Disadvantage, very time consuming, you get tired easily. Reading this type of stuff is non-trivial. Okay, and like I said, there's a whole lot of these different types of code comprehension that are covered in CS 220. All right, cannon point strategies. There's a piece of code which represents a potential vulnerability. It's user input processing, encryption handling, some other things. So we identify code patterns commonly associated with software vulnerabilities, buffer overflows, other things we trace back. So create a list of potential issues through some mechanism or process. There are tools out there that'll scan your source code and say, hey, this is a potential problem. And you could use that to say, hey, these are highlighting places it thinks there might be a buffer overflow. There might be some a type mismatch. There might be some other things. Let's look at those. There's a lot of useful tools out there that do that. They're not perfect. They don't cover everything, but they give you a start. It catches what I call the low-hanging fruit. examine the source, determine if these are relevant. You know, for example, there's tools that look for these unsafe utility functions in C. You know, get S reads a string, a line from the standard input into str. This has to be big enough to handle everything you can read. There is no bounds on this. This is potentially unsafe unless you're careful. Sprintf, take this string. No, excuse me, take this format information, these variables, and store the output in a string instead of printing to the screen. Again, lots of potential problems with this. Concatenate two strings together, copy a string from another. VSPrintf is, this allows us to have variable number of arguments of this, that all the variable arguments are stored in a list, but they do the same thing. There's a lot of different attacks, format string attacks, buffer overflows, other things. Tools will highlight, hey, we called these functions don't have bounds, you have a problem. There are ones that have bounds where it's SNPrintf, string ncat, you know, where you specify a number, or string n copy. You specify don't copy more than this. Those are still unsafe if you got the wrong number, but at least it's an attempt to be safer, and some tools may highlight those tools. But these give me candidate points. Hey, let's look where this was used. Is this a problem in this context? Maybe not. You know, I've seen, there's some code I was analyzing last year used sprintf, but it was a very well formatted format. Of the buffer was guaranteed to be the right size given everything. We could look at it. It was all checked outside the call of this. There was never going to be a problem. And so the tool I ran was running a tool to highlight it to just see what that tool did. And it said, yeah, here's a potential problem. I looked at it, no. But it was a test of how this works. So we can use an automated source analysis tool. Trace backwards code, control flow sensitive. We can look at the control flow, how the code got there, or the data, how the data got there, and figure out, did it work or not? That's one possible candidate point you're trying to do. So, like I said, there's lots of these different ways of doing this, but that's useful. Good coverage for easily identified vulnerabilities. It's not too difficult. It's hard to get off track. Results are only as good as your tool. So, I've mentioned to students before, I'll bring this up again. I think I mentioned in this class. If you use the C compiler like GCC or G++ for C++ compiler, there's a -W option that says, give me warnings. There's -W extra says, give me more warnings. Check other things. -WA all, you know, -wall, which is W all, says, give me all warnings, which doesn't give you all possible warnings. It's just misnamed. But students will run that and say, hey, you know, these are the possible warnings. Now, these tell me at least things that could be wrong in my code, things that could cause vulnerabilities. And they put more and more security checks just in there. It's a first pass. That's saying, hey, there's a potential problem. It may tell you, hey, you're using this as sprintf function. That's potentially vulnerability, etc. There are tools that are recommended by people. If you're building websites or other things, use this tool. And they're useful. We run experiments on them, find they miss a lot of things, but they also get things. So that low-hanging fruit. So our candidate point again, piece of code represents potential vulnerability. The strategy creates a list of potential issues through some mechanism process. Examine the source code to determine the relevance of these issues. Simple and fast. Strategies don't encourage a strong understanding of the code. They ignore vulnerabilities that don't fit the rather limited candidate point definitions. They're a quick and easy pass. They're the type of things a company should be able to do by itself before hiring somebody to do external audit. It's the type of thing that developers or testers should be able to do. If I go back to website, there's standard tools out there to check your websites for certain types of vulnerabilities. There are programs out there, bug bounty programs, okay, which allow you. Companies will post information, say, hey, we want you to examine our website. We want you to examine our code. If you find a vulnerability, send us information about it. And if it's a really bad vulnerability, we'll give you lots of money. If it's an okay vulnerability, not really bad, but it's still moderate severity, we'll give you some money. That's nice. Some people make a lot of money doing this. Other people spend a lot of time going down rabbit holes and don't make any money on these things. But they're useful programs because they're crowdsourcing the idea of, doing our testing. They say on most of those, don't run the standard tools, the vulnerability analysis tools or whatever. We're doing those already. Don't waste your time and don't give us, oh, hey, we ran this output and it's saying all these possible vulnerabilities. Here it is. This is all these candidate points. We know about these. We've already checked them. And they don't care. You give us a list of, hey, here's all the places you could have a problem. I said, no. Show us the input to our program that causes it to crash. Show us the input to our program that leaks that sensitive data. And I've seen some which says, it's I don't know what it was, some type of crypto system that says, we've encrypted on our website this file. If you can tell us the contents of the file, yeah, you won. And we'll give you the money. I do know one person who found a vulnerability in a common library. And then he did what you're not supposed to do, but he got away with it. He found all the companies using that library and sent bug reports to each of those companies. And each of them went, wow, you found a vulnerability in our code. Okay, here's the fix. Here's the payoff. Here's the payoff. Until finally someone said, wait, that's a common library. That's their fault. We're not going to pay you. All right. Static code analysis. I was talking about this, also known as source code analysis, usually performed as part of a code review carried out at the implementation phase of a security software development lifecycle, commonly referred to as running a static code analysis tool that attempts to highlight possible vulnerabilities within the source code. Okay, let's look at the source code and just analyze it. Don't run the program. Don't test the program while it's running. That's a dynamic analysis. Just look at the code and see if you got something wrong. That's static analysis. It scales well. It can be run on lots of software. It can be run repeatedly, like in your nightly builds, as we're updating the software and we're retesting the software and rebuilding the executable software. We're also looking at the source code and running this analysis every night. For things that such tools can automatically find with high confidence, they're great. But many types of security vulnerabilities are very difficult to find automatically. High numbers of false positives. Hey, you use this S/F function here, and here. And this is a potential vulnerability. No, I did it the right way each of these places. It doesn't matter. Many tools have difficulty analyzing code that can't be compiled. If the code is not complete, so that you can't actually build and compile, the tools are not going to find your problems. Oh, shoot. I went faster than I expected. I will come back to this one next time. Okay. But here's an example. You can go and get this thing called Flaw Finder. Install it, but this test.c was the thing we had to do. Flaw Finder runs, yeah, I don't even have the link. Flaw Finder runs, and it's one of these standard tools that's recommended for use by a lot of people. You have to use Python for this. It's written in Python. Pip is a Python package installer. So if you're doing this in Linux, you can install Python pip and then use pip. The sudo means run this as root, so it's full install permissions. You install Flaw Finder, you can run Flaw Finder on your test case, it'll give you possible errors. I'll come back and show that. I forgot my laptop. Like I said, I didn't think I was going to stop right before this, but because I started elsewhere. Okay. Now that you've done, let's assume you've done static analysis. Let's assume you've done the best you can there. Now you do your dynamic analysis, your testing. run the software. Does it behave correctly? It's going to be on some finite set of test cases because we don't have infinite amount of time. These are usually selected from the infinite execution domain. What most companies do, if they are doing adequate testing, is they build up a test suite. And they say, this is the inputs, these are the expected outputs. And every time the code is modified, they do nightly builds. They recompile the code on a separate server. Version control management system, everything. I modify the code, I submit it to the system. It gets submitted into this nightly build. They run the build. They run all the tests on this newly compiled version of the code and make sure nothing failed. What happens if something failed? You get a report. This code failed. If you worked at, well, I won't name the company's name. There was a company, and this was several years ago, who got tired because developers, instead of testing their code rigorously, the changes they made before submitting it to nightly build, they make their changes, submit to nightly build, and we'll get a nightly build report and tells us, oh, these are the bugs, and then we'll work on it the next day. But if your code was so bad, it may have broken his code in the portion of the same system, so you'd get the reports, he wouldn't. So they decided that was a bad thing. So if you broke the nightly build, you got a black balloon flying above your desk. And this was in a place with a whole bunch of cubbies, so everybody could see this black balloon because you had like 100 different cubby holes in this big workspace. And until the next person broke the nightly build, you kept that black balloon for at least a week. The number of nightly build crashes went way down. People learned to test things more rigorously before submitting them. When shortly before I started programming, people used punch cards. And so the same type of thing, you submitted the punch card, it ran at some scheduled time, and then you got your error messages. It took forever. Once we got to be doing things interactively, so people planned a lot. They spent a lot of time analyzing their code to make sure it would work because they didn't want to, okay, I got my time on the computer tonight. I spent all this time working on it. I get, twice a week I get to run on the computer and it broke. Now I got to wait till the next time. Once it got interactive, people planned less and just, hey, hit compile, see what happens. I bet that's, for those of you who are running right now, that's what you do. Now I'll just write the code and see what happens. Oh, there's a typo. Oh, there's a missing semicolon, all that. I don't look at my source code to see if these things are happening. I let the compiler find it for me. But that means the things that are syntactically correct, that compile correct, but are still wrong, then you miss, unless you run these tests. So you build lots and lots of these tests, and you run them again and again and again. We call that regression testing. You would have the same set of tests, you run them again and again as you modify and improve the code. Okay, like I said, this is dynamic testing. You're executing the program on selected inputs. Where static code, again, you're just running an analysis tool on the source code. Okay, look at these are some different types of testing. Smoke testing, known as build verification testing, is a type of software testing comprised of a non-exhaustive set of tests that aim at ensuring that the most important functions work. You're just looking, did the thing compile? Do the most important functions work? Functional testing, where now we look against certain functional requirements, certain specifications of the system. These are the functions we want to test. And typically what I see is people will break them up into different units, different groups of tests. These are testing opening connections. These are testing encrypting files, decrypting files, compressing files, whatever you have to do. Usability testing, much harder. This usually isn't automated. This is end user perspective, determine the system's easily usable. So you have a group of people sit down and try and use your code. I don't believe Microsoft actually does this. Now, I know they actually do this. I don't know who they bring in, but the changes to some of their interfaces drive me crazy. Security testing, we intend to uncover vulnerabilities in the system, determine that data and resources are protected from possible intruders. We're just looking at security capabilities, not full functional capabilities. Performance testing, how fast does it run? How cleanly does it run? How, you know, how responsive is it? How stable is it with respect to a certain workload? Regression testing, I mentioned that. Changes, enhancements, defects don't adversely affect. So basic have not adversely affected it. We have things that worked in the past, do they still work? I don't know how many times I've run into things like that. I did one, we were working on the Cyber Grant Challenge thing, and it's like, oh, we have this great idea. Now I learned a lot with what we were doing, or reinforced what I had learned in doing. We made a change. We had a hypothesis. If we do this, the code will be faster. And since we were working on hundreds of input programs that we had to test each thousands of times, speed was of the essence. And we're under a clock. So we'd make an assumption. Oh, if I do this, it'll be faster. I know this will be faster. Then we'd run our performance test. And, oh, it was not faster. Or, oh, on average, it was faster, but the worst case was much slower. And we definitely wanted our worst case to be no slower than a certain balance. So we'd highlight the code, we'd comment out the old code, put in the new code, or I just have a different function. Here's the function that does it. Here's the new version of the function. So I'd rename the old version of the function, that function name underscore old. Put in the new one, run it up, didn't work any better, get rid of the new one, put a little comment in there above the old one, this still works better than this, and move forward. And we did regression testing with all these. Did we break anything? Because sometimes I fix A and I break B. And especially with what we were doing there, where we were taking code, modifying it, reassembling it, rebuilding it, re-executing it. This happened all the time. We'd fix A and break B. Or we'd fix B and break A, or something else. Compliance testing. Are you conform, if you're matching a protocol, if you're implementing some type of system, encryption system, are you doing the right encryption? Are you doing it correctly so that anybody else with a different version of the same code can decrypt your code? We're doing network protocols. Are we following all the requirements? Lots of that is out there that people do. So how do we test it? Well, if we look at it in the big picture, we have black box, white box, and gray box testing. Black box testing, you know nothing. It's as if you're the customer, you have the code. They can be functional or non-functional tests, usually functional. I'm just trying to see, does it do what I expect it to do from the outside, but I know nothing about the inside. White box testing actually knows something about the internal structure, design, implementation. I have the full source code. I have everything. I can really focus on my testing. I can even do unit testing by taking pieces of the code and testing them independently. I can take a piece of code that I want to test, write another piece of code that links and uses that function independent of the main program. Gray box testing, it's a combination of black box testing, white box. You interact with it as if it's a black box, but you know how it's processing, so you can follow through and say, oh, this is where it's getting stuck. If I change the inputs this way to move forward. We'll come back to that in a second. Fuzzing, I like fuzzing. It's a software testing technique which uses a tool, a fuzzer, to randomly generate inputs or to take standard inputs and mutate them, modify them some way. The inputs then fed to the programs and the program runs. And the goal is to crash the code. That's the main program. Normally input strings, if you do it this way, and you're creating random input strings, it'll say, that's not valid. That's not the format I wanted. So it checks all your error checking. And normally the program would just say, yeah, I'm done. It's not a crash, it just terminates, or it just asks you for a new input. Okay, but sometimes you can get it to do weird stuff. So Barton Miller generated this idea to test some standard Unix utilities. 25 to 33% of the programs were successfully crashed by the tool because they didn't do adequate error checking because they assumed people who were using the tools knew what they were doing and wouldn't put in the wrong format input. Right? Because people want to use my tool. If they want to use my tool, they're going to use the right inputs. But then this leads to problems if people want to use your tool not the way you wanted them to. And they don't use the right inputs and they get your tool to do things that it shouldn't be, especially if your tool runs at the supervisory level. It runs as root, and then it can do lots of things. Problem is some parts of the code aren't hit by a fuzzer because it requires special input values, because it needs to follow a specific path through your code to get to the way down here. There's one module that has the fuzz, but you have to have several right inputs. You know, hey, there was one I was looking at, which was creating a messaging system. So you had to create 2 different users with 2 different usernames, then have user or 3 different users, then have user A send a message to user B. Then user C would enter a message of the right type and would get the results of the message that wasn't sent to them. But you had to enter all this data into the system to configure it, to get it running first, using all the right usernames, and then the right message ID for the attack before you could do this. Randomness would never get you there. Oops, that should be black box. Traditional fuzzing, black box, random input. Smart fuzzing, guided by other techniques. Hey, we're fuzzing a PDF file viewer. Smart fuzzing says, oh, I'm going to create variants of PDF files. I'm not going to create movie files or JPEGs because those don't matter. Excessive performance fuzzer depends greatly on the information available to them. So if source information is available, program's expected input format is known, that all helps. Fuzzers work much better in gray box, where they have the source code. Can require a lot of processing time, may not reach code hidden behind complex sequences of if-else conditions that the fuzzer fails to guess. The longer you run, the more bugs you may find. 24 hours is a typical estimated time for running fuzzers. Let's see. I'm going to actually go to, where's my website? There it is. I know I'm not sharing this yet. So FuzzBench is a tool for testing fuzzers. And so they have these different fuzzers, AFL++, optimal, Hong fuzz, entropic, LawFintel, libfuzzer, AFL smart, AFL is American fuzzy lop, mopped, AFL fast, fair fuzz, eclipser. So they got different fuzzers. They have on the right several different libraries they experiment with. And the idea is, how well are they finding things? And so this report shows examples, says, hey, we're going to look at this fuzzer and we're going to look at the region coverage, how much of the code they covered, and we're going to rank them. So on this one example, in the bloaty fuzz target summary, and we run the fuzzers many times. And so each input, there's a range of how much the code it covers, and you can see code coverage growth over time. So basically, this one took a while, but started covering more, where this top one, this gray one, really quickly. So this was after 9 hours, 15 minutes here. This after 15 hours. So 95% confidence it covered this much code. So, okay, tells us how much code it covered, it looked at, that's cool. If I actually look at the code coverage for, say, AFL fast, here's the actual file, bloaty.cc, bloaty.h, etc. Well, covered 49% of the functions in here, 60% of the functions in here, 97 in there, that's good, 100% here. Oh, look at all this stuff that was never touched. 100% here. So we get down to the bottom, see, code comprehension. You got to understand all this code. They covered 12.4% of the functions. 15.5% of the, what's that? I think that's lines of code. So I look at the graph, this one thing that bothers me, I see these charts, I say, wow, this did pretty well. Yeah, it got up to 15%. Okay, which I lied, that was mopped. Let's actually look at mopped. Mopped probably did better. Got up to 15.59%, oh yeah, 12.4%, pretty much the same. So we see these things, we see these reports, and this is the problem, that somebody could give this, somebody could give this to me and say, hey, we ran the fuzzer, this is how well it did, we took the best fuzzer, we ran this, we got this, here's our code coverage report. We didn't find any vulnerabilities. And you'll say, oh, good, here's your money. And then they find out you only covered 15% of my code. I'm picking on this because I've gone to several conferences where I see these charts and I say, but what's the maximum possible? Yeah, I got 9,000 edges out of this, but there were 100,000 edges. Or there's 75,000 edges, but you don't show me that because you don't tell me that. So be careful. You run the fuzzer found nothing, but did it look? There's a lot of research into making sure we actually found where it hit. And I'll talk about that next time. Did it hit the right part of the code? Is it doing what I want it to do? There's a lot of code that's never tested. One of these libraries in here was using the zlib library, which is a compression library. And there's a whole section of code that none of the fuzzers touched. Why? Because that was only executed if you called it in the context of gzip. But if you called it in the context of the standard zlib, it never executed because it was a different file format that it was using. And the test case they set up never set up for the other one. It wasn't possible. No fuzzer, the way it was running, and I'll talk about this later, but it was ever possible it could run that code. Because it was based on the name of the function, call it the file, the executable file. And they didn't name it gzip. They named it, zlib tester or zlib fuzzer test or whatever. And then so it said, oh, I'm not gzip. Don't run this special code that only run if I'm running gzip. We're very, very unique. So nobody ever fuzzed it. It does have a bug in it. I have no idea. I should have rerun it, but I don't want to run the fuzz batch. So anyway, thoughts, questions? Out there, yes.
So like you're saying that it's just people are only going to really short percentage of the fuzzer or whatever it is. Is there like a lot of I guess bait and switch in the cybersecurity kind of industry? Like,
Is there a lot of what?
bait and switch? Bait
and switch?
Yeah. Where people are advertising certain services and because they're somewhat confident that
I don't know if it's really bait and switch or just overselling.
Okay.
Hey, I've done this training, I have this tool, I have this capability, I have this magic bullet that's going to solve everything. It's not true. But it's not like they're marketing something they know absolutely doesn't do what it does. It's more that they are overselling. And both researchers publishing, hey, we solved this tool, we did all this. I had one I'll talk about later, dealing with SQL injection attacks. They say, yeah, we can find this. And it's like, no, you can't. It's not possible. Here's why it's not possible. They published it in their paper. They bragged about it in their dissertation. They were wrong, but they didn't deliberately do it. Yeah.
Well, like you were saying earlier, bad guys like to steal.
Uh-huh.
Do other nations have this issue or is this something to
Oh, this is worldwide.
this worldwide?
This is worldwide.
Okay. Okay.